Okay, so now we're moving on to Chapter 4. And Chapter 4 is the largest chapter that we cover. In a number of ways, we can kind of think of it as the main chapter for this course. So we start off in section 4.1 with a discussion of real vector spaces, which I'm really just going to refer to them as vector spaces. The term real here just concerns the scalars that we use with vector spaces. They're assumed to be real numbers. When we talk about scalars, like we have been up until this point, we're talking about real numbers. However, in the bigger picture, we don't actually need scalars to be just real numbers. In fact, I think I mentioned at the beginning of this course, linear algebra gets much more interesting when you allow for the discussion of complex numbers in these vector spaces. So talking about complex scalars is a more, in my opinion, a more interesting thing than what we're going to be able to do in this course. But that's okay. That's for a second course in linear algebra if you ever need that. So let's talk about what we mean when we talk about a vector space. First of all, from chapters 1 through 3, we've been developing, among other things, we've been developing the concepts of matrices and what we've been calling vectors in Rn, in n space. In the process of covering those different things, we've developed a number of properties for those types of entities. So it's worth noting that both matrices, m by n matrices, and vectors in Rn satisfy a number of the same properties. They also, we can also perform operations on them in a number of similar ways. So to be specific, take two m by n matrices. We can add them to produce a new matrix. Take two vectors in Rn. We can also add those to produce a new vector in Rn. So both of those systems, whether it's m by n matrices or vectors in Rn, have an operation called addition, and they produce new entities in those systems. They produce new matrices or new vectors. We also have an operation called scalar multiplication for both of those systems. We know what it means to multiply a matrix by a scalar, and we also know what it means to multiply a vector in Rn by a scalar. Now, aside from just those two operations, we also have a number of properties that those operations and those systems hold. So, and I want to be careful with the word system. I'm going to be replacing that word with vector space. I'm not talking about systems of equations. I'm just talking about a mathematical object, I guess. So let's take the concept of addition, for example. When it comes to both matrices and vectors in Rn, the addition operation is commutative. U plus v is equal to v plus u. In both of those cases, it's also associative. We have a number of other interesting properties. The homogeneity property, which concerns scalars, what we can do with scalars. We have a distributive property where scalars will distribute over matrix or vector addition or matrix addition, and other similar properties. So having dealt with two different sets of objects, either m by n matrices or vectors in Rn, we see that they share a number of interesting properties. And in math, in higher mathematics, one thing that mathematicians do is they look for various mathematical objects that have a shared set of properties like that. And they ask the question, can I generalize this? Can I define a more abstract object simply by the properties that it satisfies and then prove things about that product, that concept? And in the case of linear algebra, where we do that is in the definition of a vector space. What we're going to do is take those two systems as our prototypes take the set of m by n matrices with its operations of addition and scalar multiplication, and also the set of vectors in Rn with its operation of addition and scalar multiplication, which, by the way, are not the same operations. Adding two matrices, even though it has similarities to adding two vectors in Rn, is technically defined in a different way. So what we mean by addition depends on the set of objects that we're talking about. Same thing with scalar multiplication. But what we're trying to do in this section is take those two prototypes and generalize. So basically, we're going to do this. I'm going to go through this definition with you. Let's suppose that V is some arbitrary non-empty set of objects. Non-empty is important, and objects can mean anything, right? When we did a preliminaries section at the beginning of this class, we talked about a set, which can be a set of literally anything. And on this set, we're going to define two different operations like we did with matrices and vectors in Rn, addition and scalar multiplication. Now, when we say addition, we're going to be using a plus symbol. But one thing you need to be extremely careful about, and this is a major snag for most first-time linear algebra students, is you have to get away from the idea that this addition operation means the same thing as the addition that you're used to. It's just an operation that is used to combine two vectors to produce a new vector. But what we mean by that addition is entirely dependent on how we define it in an example. So right now this should sound very vague, and we'll illustrate this better with some examples. But we can take two vectors and perform this operation, which we're going to call addition, but is not necessarily the same addition that you're used to. And it can produce new elements in V. We call these elements of V vectors, by the way. And we can refer to the object that we get by adding them as the sum of those two vectors. And then we also are going to define another operation that takes scalars, which are going to be assumed in this chapter, in this book, for our purposes, to be a real number. And we define a different operation that multiplies vectors in V by scalars, which I'm gonna call K here. Okay, basically that just means KV is a scalar multiple of U, and that's some other vector that lives in V. Okay. So if V is going to be this thing that we call a vector space, it has to be a non-empty set of objects. It has to have these two operations, addition and scalar multiplication, which again, both of those can mean very different things than what we're used to depending on what V is and how we define addition and scalar multiplication. And then in addition to that, we have to have these 10 properties satisfied. Now we call these 10 properties the vector space axioms. And all we mean by the term axiom in this context is a property that this thing has to satisfy in order for this to be a vector space. So I'm going to briefly go through these 10 axioms, and I'm going to give names to some of them. So the first one, if U and V are objects in V, then U plus V is in V. What this means is a non-empty set V is that satisfies this property. We call this closure under addition. Okay. So that closure under addition means that if we add any two vectors in this set, the result is another vector that still belongs to that same set. You can't add any two vectors in this set V and produce something that exists outside of V. That's what that closure property means. Here, axiom 2, we have to have the commutative property for addition. So U plus V should always equal V plus U. 3 is the associative property for addition, which we are familiar with from our matrices. We showed that it had this property, vectors in Rn. Real numbers have this property with real number addition. That has to exist in any vector space as well. 4, there has to exist some object which we're going to notate by a bolded 0, and we call that the 0 vector for V. and it satisfies this property. 0 plus u equals u plus 0, which equals u for any u in V. 0 is also known as an additive identity, and we've encountered examples of 0 vectors in the previous sections. If you have an m by n 0 matrix, that satisfies this property, where u would be thought of as a matrix. The 0 vector in Rn satisfies this property. That's why we still call it a 0 vector. You need, just like the whole rant that I went on a little while ago about being careful about what you think addition is in the context of a vector space, you also have to be extremely careful with what we call a 0 vector in a vector space. A 0 vector may not look like what you think it looks like. It may not look like the number 0. It may not look like a matrix with a bunch of zeros as entries. In fact, we're going to do one example towards the end of this section where we're going to show that an oddly defined set is in fact a vector space under very specific operations of addition and scalar multiplication. And we're going to prove that the 0 vector for that vector space is the real number 1. Yeah, we're going to show that 1 is 0 in that vector space. That sounds very confusing, but again, when we talk about the 0 vector, we're not necessarily talking about a number that represents nothing. That's how we normally think of 0, and that's not a sufficient way to think about 0 anymore. It's simply an object that has this property. That's how we're supposed to think of it. Okay? I feel like I'm ranting too much about this, but these are actually very important concepts. Axiom 5. For every vector u in V, there's an object that we call negative u in V. Your book calls this the negative u. You can also call it the opposite of u. You're going to find that I like to call it the additive inverse of u. All of those are valid terms for this. And it's an object that when added to u in either order, u plus negative u or negative u plus u, produces the 0 vector that was defined in the previous axiom. And again, this 0 vector may not look like the number 0. Okay? So whatever this 0 vector is, this is a property that needs to be satisfied by a vector space. Now, sometimes you'll hear me call this axiom closure under additive inverses or closure under inverses. And just all that means is that every vector in V also has an inverse that's also in V, such that their sum gives us the 0 vector. Okay? Axiom 6, we call this closure under scalar multiplication. Let's see if I have enough room for this. Multiplication. What? Multiplication. I can't spell. Okay? So it's one of 2 closure axioms or closure properties that vector spaces have to have. And this is defined in a similar way. If you take any vector u in V and multiply it by any scalar k, then the result ku has to still be a vector in V. Multiplying u by some scalar can't take us to a vector that's outside of V if V is going to be a vector space. Okay? And again, I cannot emphasize this enough. Even though up until this point we've been referring to scalar multiplication in a specific way, scalar multiplication with matrices, scalar multiplication with vectors in Rn, do not assume here that this scalar multiplication looks anything like what you're used to. We haven't defined this in this general abstraction of the idea of a vector space. It's just an operation, okay? These other properties here help us with the algebra of working with vector spaces. So this one says that scalar multiplication distributes over vector addition. Also, if you have a sum of 2 scalars here, k plus m, and you multiply that sum by u, we get a version of the distributive property where u distributes into that sum of scalars. We have something that looks like the associative property, but is technically not. This is copied from your book, and there's a typo here. That m should not be bolded. It's supposed to be a scalar. Only the u should be bolded in each case. And what this says is if I have a scalar k times a scalar multiple of u, so I would do mu first, I get the same result as if I just multiplied the 2 scalars together first and then multiplied that to u. then finally, this last axiom says that multiplying by a scalar, specifically the scalar 1, should act like multiplying 1 in the real numbers. So in other words, multiplying any vector by the scalar 1 should leave me with that vector. In other words, multiplying by 1 should not change anything. Okay? This is a list of properties. It's not suggesting anything about what V looks like, what kind of objects it contains. It's up to us to find specific examples of sets of this type with these two types of operations that satisfy all of these properties to be able to call them vector spaces. So let's move from the abstract into the slightly more concrete, and let's talk about several very, very important vector spaces, some of which we've been dealing with already. So Rn, which again, that's Euclidean n space, under the already previously defined vector addition and scalar multiplication, that's a vector space. We defined that a while back, and we've actually proven, or at least shown theorems, stating that all of these properties are already true. So there's nothing more to prove there. We've done the work on that. Now this one we haven't talked about, but you notice it looks like Rn, but with an infinity here instead of an n. And it's pretty much exactly what you would expect that to mean. It's the set of all sequences of real numbers. You can think of it as an ordered infinity tuple if you want. It has an infinite number of components. That's what the ... here means. But really what those are sequences, which you deal with in calculus 2 and stuff like that. But what operations do we define on this? Remember, a set by itself can't be a vector space. You have to define a couple of operations on it first for it to have any chance of being a vector space. Specifically addition and scalar multiplication. So we define addition and scalar multiplication of sequences in the same way that we define them for Rn. We add two sequences by adding their corresponding components together. That gives us a new sequence. We multiply a sequence by a scalar by multiplying each of its components by that scalar. Okay, so it looks very, very similar to Rn, and it behaves in a very similar way as a vector space. Here's one we haven't talked about yet. That's a capital F with a closed interval AB here. This is the set of all real valued functions on the interval AB, where addition and scalar multiplication is defined by the usual addition of two functions. So you do a lot with this in algebra and calculus. You know, adding two, if you add f of x plus g of x, the result is a new function that we just call f plus g of x. Similarly, scalar multiplication in this case is just the usual multiplication of a function by some constant k. So this set of functions you have spent years working with. You've just never called it that. You've been working with these in algebra and calculus 1 and calculus 2. So this should be some familiar territory here. Okay. In the same vein, if I, instead of using a closed interval AB here, if I use open parentheses, negative infinity to infinity, remember that's the interval notation for the real line. So this is a similar set. We just define this to be the set of all real valued functions that are defined everywhere on the real line, their domains are all real numbers. And we use the same operations as FAB. Same thing, you know, adding two functions the way we do here, multiplying by a constant the way that we do here. Now, notice I'm not proving that these are vector spaces. All I've done is I've defined the sets and their operations. And proving that something is a vector space is a long task because there's 10 separate axioms to check. In this case, you know, in the case of either of these sets, I can kind of look over some of these axioms and mentally check them off and say, yeah, I know that that's true for this space. So, for example, let's suppose that we're looking at the space, the set of functions that are defined on the interval AB. If I take two functions that are defined on that interval and I add them together, I know that the result will be another function that's also defined on that interval. That's a basic property of functions. You can add two functions and produce a new function, basically. So we get that closure property. I know that because the sum of these two functions, if you pick a specific value of x, for example, plug it into each function, the result in both of these cases is some real number. That's what it means for it to be a real valued function. But real number addition is commutative. So that it stands to reason then that these two functions can be added in either order, and it doesn't change the resulting function. So that's telling me that I get the commutative property. Similar argument can be made for the associative property. What is the zero vector in this space? Well, we're going to talk about that down here, so I'll wait until we get there. And then, you can kind of mentally check off the rest of these properties if you want, and see that with these operations, this set of functions satisfies all of the necessary properties to be a vector space. So what that means for us is actually in the context of linear algebra, we get to think of functions as vectors. And that might be a little bizarre. You might not be used to thinking of functions as vectors, but under this definition, they can be thought of that way, and we are going to call them that. The set M(m)n, so remember this is the set of all m by n matrices, is a vector space with the already defined operations of matrix addition and scalar multiplication. And again, we've already verified all of the vector space properties back in chapter 1 where we derive all of that stuff from matrices. So there's not anything more to do here. Finally, if you have some vector space V, and again, if V is a vector space, one of the axioms says that we have to have a zero vector in that space. So if I look at just the set containing that zero vector, that is a vector space in its own right, and we call that the zero vector space. In section 4.2, we're going to change the name of that. We'll start calling it the zero subspace. And that's not too hard to see if you come here and you look at these properties. Again, this set contains only that one vector 0. So how does that interact with these properties or these axioms up here? Well, if u and v are any objects in that zero vector space, which means u and v would both have to be 0 since that's the only thing in there, is it true that 0 plus 0 is in that space? Well, yes, because 0 plus 0 is 0. So we still have that same object in there. You can similarly verify all of these. Okay. In some cases, we also call this the trivial vector space. All right. Down here at the bottom, we want to take these three examples of vector spaces and identify the zero vector in each one. So here, this is the set of all 2 by 3 matrices. We already know that the zero vector in this space should look like a zero matrix with 2 rows and 3 columns. And we've verified this before. If you add this to any other 2 by 3 matrix, it doesn't change that 2 by 3 matrix. So that makes it function in the way that a zero vector is supposed to function. What is the zero vector in this space? Well, in the set of all functions defined everywhere, it's the constant function, f of x equals 0. And again, you can verify that by looking at how we define addition, because that's what gives meaning to a zero vector. If I take any function, f of x equals, say, cosine of x or something like that, if I add it to the constant function 0, then I get cosine of x still. Or if f of x is anything and I add it to the 0 function, I still get f of x. So this is our zero vector. Now you need to be careful with this because oftentimes when dealing with functions, we don't always write f of x equals. We oftentimes just write what the function is equal to, cosine of x or e to the x or whatever. However, I'm paying special attention to this, f of x equals 0, because there is a difference between a constant function 0 and the actual constant 0. This is the output for every input that I plug into this, whereas the constant 0 is just a number. Okay, they look the same, but they're thought of differently. Finally, R infinity. What do you think the zero vector for R infinity would be? Well, we know the zero vector is for Rn, so it makes sense that the zero vector for R infinity should look similar. It's just the sequence of zeros. This is oftentimes just called the zero sequence. All 3 of these are zero vectors, but each one looks very, very different. One is a matrix, one is a function, one is a sequence. They all are defined, or they all fit the definition of a zero vector in their respective vector spaces. Now you might look at this and say, well, each one of them, even though they look different, has the scalar 0 in them somewhere. So it must mean that zero vectors always involve the number 0 somehow. But I've already said we're going to see an example later where that's not the case at all. So you have to be careful with your concept of zero vector. Okay? I know I spent about 25 minutes almost on one page, but this is the driving concept for the rest of this course, this idea of a vector space, and so it was worth spending a lot of time on it. We're going to continue on in this section in the next video.